Hello, there we are. Hello, and welcome to the next talk, the last talk of the day, which is about architectural archipelagos. And I had to practice how to say that word, architectural archipelagos, with Marcelo Schmidt-Lasser. Please go ahead, Marcelo. Thank you.
Thank you very much. And so my name is Marcelo Schmidt-Lasser. I am very impressed. You're one of the first people who gets my full name all correctly. And I'll be presenting our work on architectural archipelagos. So the first thing I want to pose before I really start my presentation is the question, do we, in the software engineering research community, make good software systems? So there are several different quality metrics that we can use to try and answer that question in a empirical and scientific manner, but just in an informal way from the perspective of technical debt, I think we can all agree that the answer is unfortunately no. Academic research software tends to accumulate a very, very large amount of technical debt, which either tends to not be repaid at all, or the effort to do that repayment becomes so great that the tools themselves are dropped and rewritten from scratch. Now, we looked at a few of the reasons why this seems to be particularly pernicious within the academic environment, and we found a few important differences. So first, we are in a different environment from industry or open source development, which are the areas that the technical debt community and the software engineering community focus most of their research on. Within academia, we have just different cultures and different types of people involved in these projects. We have different goals. Academic research software is intended to answer research questions, not to fulfill requirements. And so the entire development process has to be tailored around that difference. We follow different processes. There are not many processes that come out of the software engineering community that are made specifically for academic environments. And if there are, very often we just don't follow them and create ad hoc processes of our own. There's different team composition, and this is an important one because the turnaround of team members and the team size in academic research software development is very different. It's dependent on the presence of graduate students for the most part. And when these graduate students graduate, they finish their masters or PhDs or postdocs, they move on and either take their work with them, which means they need to train an entirely new team of people, or they leave their work behind, often without any significant documentation, and then that in itself generates a lot of technical debt that needs to be repaid before anyone can even start working on it. Finally, there's the publish or perish culture within academic research, which encourages the accruement of technical debt towards being able to publish a piece of work, and doesn't really put much value on the software artifacts themselves. There's been a lot of initiatives recently, like the ACM replicability badges, to get more value placed onto the software artifacts. But as it stands, we don't have much solid evidence that this is really solving the problem. So as I mentioned, all of these things, they lead to an enormous amount of technical debt being accrued. But the question is, how do we improve that? Now that I've outlined all of these causes for differences, for different causes of technical debt in academic research software, how do we make it so that in the future academic research software is better, is more viable both for replication for other research groups to put into use and for adoption by industrial groups. So the approach we took was essentially the same approach that software engineering tends to take with these kinds of things. We looked at existing success stories and we tried to distill what went right and what went wrong within those kinds of systems. And we looked specifically at a class that we have named the 3L Arts class, that is large, long-lived academic research tool suites. Specifically, we looked at two tool suites that we are very familiar with: Arcade, which is the Architecture, Recovery, Change, and Decay Evaluator tool suite, and the C2 framework for component and message-based systems. We've come to several conclusions that I will touch on in a moment, but it's important to note that the conclusions that we've seen and the characteristics that we've seen here, they apply to a lot of research off-the-shelf tools that we've worked with, and they've been corroborated by colleagues of ours working on similar 3L Arts projects. So it's not specific to the work that our group has done. And what we came up with was the idea of the architectural archipelago. Now, the idea here is we have a set of islands within a tool suite, each one of which has been developed by probably a different person and implements a different piece of functionality. And these pieces of functionality, these islands, are not necessarily interdependent with every single other island in the system. There is a certain sort of tree structure here where one island can be extended into another island, and then that other island extended into another two, and then the dependencies that they have are related directly to what they are extending. So, for example, and I'll be quick here, there is the idea of an origin island, which is the system or tool that started the entire archipelago. Then you've got major and minor extensions, which are extensions that significantly change the functionalities of the system, or extensions that just enable some minor things like a new I/O port into an existing component. We've got distance, the concept of distance from extensions. So how far away from the original architecture they are, how much drift they introduce into the tool suite. And we have the idea of extensions to extensions. So an extension is itself an island, and that island can have islands pop out of it. We give a lot more details in our paper, and we correlate this with the two case studies that we've looked into. So I will close there because we are a bit short on time. Thank you very much for watching the presentation, and please reach out with any sorts of stories that you might have or tools that you might want to suggest for us to have a look at, since we are really interested in gathering more data about this and better understanding these phenomena that happen in the academic field and which generate so much technical debt in our tools.
Thank you so much, Marcelo. Thank you for your talk. I appreciate it. I'm going to ask any questions for Marcelo in discussion to go to the discussion room that Zadia just put the link to in the chat, so that I have a few seconds just to wrap up today. This ends the first day of Tech Debt 2021. Thank you all so much for being here. Thank you to our presenters, to our panelists, to our organizing committee, and most of all to the attendees and participants. Thank you. Have a lovely afternoon or evening or night, whatever faces you, and we will see you tomorrow. Goodbye.